So in this video, we're going to consider double angle identities. This relates directly to our compound angle identities. But we end up with a double angle when angle A is equivalent to angle B. So let's consider the identity of sine angle A plus angle B. So if A is equal to B, then essentially we're going to have the sine of angle A plus angle A, which means that we can write this as the sine of 2A. So really what this ends up saying is we've got the sine of A times the cos of A plus the cos of A times the sine of A, which essentially means we've just got two lots of the sine of A times the cos of A. And what we've created here is a double angle identity, the sine of 2A. Let's consider this if we had cos A plus B. So again, if A and B are equivalent, we would end up with the cos of A plus A, or cos 2A. So this is equal to cos A times the cos of A, subtract the sine of A times the sine of A, which we can write as cos squared A take sine squared A. Now, because we've got the sine squared and cos squared involved here, we can also manipulate these further using our Pythagorean identity. Let's consider first if we replaced the sine squared A with 1 minus cos squared A. So we'll keep the first cos squared A, and we're going to subtract 1 minus cos squared A. Well, this is equal to 2 lots of cos squared A subtract 1. And what this gives us is an alternative for the double angle identity involving cosine. Let's consider if instead we replace the cos squared A with 1 minus sine squared A. So we've got 1 minus sine squared A take sine squared A. Well, this is equivalent to 1 minus 2 sine squared A. And again, we have an equivalent alternative to represent the double angle identity involving cosine. Now let's consider the compound angle formula for tan. So again, if A equals B, we're going to have the tan of 2A. So this is going to be equal to tan A plus tan of angle A divided by 1 subtract tan A times tan A. So we can simplify this to 2 tan A over 1 minus tan squared A. So we've just got some more identities that we can use when we're trying to solve or prove. Just a note to be aware of is it seems that in all of these double angle identities that the angle on the left-hand side, so let's use the tan to represent this, which is 2A, is always double the angles involved on the right-hand side, as I've highlighted in green in the tan 2A example or identity. So if we consider this, this means tan 2A on the left-hand side is going to be the sine A times the cos of A. So we've just got the singular angle on the right. So if we had, for example, sine of 4 theta, this would be 2 lots of sine 2 theta times cos 2 theta. Or if we put an angle in, the sine of 60 degrees is going to be 2 lots of sine 30 times cos 30. So we have the double angle on the left-hand side of the identity equates to just the single angle on the right side. So we can start calling these half-angle identities. So if we take that idea that the sine of 2A equals 2 sine A times cos A, then the sine of theta is going to be 2 times the sine of half theta times the cos of half theta. So let's keep this idea that we can have a half angle identity involved just as much as a double angle identity involved. Just makes our identities more versatile in their use. So let's take a look at some questions. So if the sine of A is 4/5, where the angle A is acute, let's determine the value of the following. So we've got a trig ratio here, so I'm just going to draw myself a triangle to recognise that if we're looking from angle A, the opposite is 4, the hypotenuse is 5, which means the adjacent side is going to be 3 with our Pythagorean triple. So the sine of 2A is represented by 2 times the sine of A times the cos of A with our double angle identity. We can evaluate this. It's going to be 2 lots of 4/5 times 3/5 using our right triangle. And this is going to equal 24/25. Now the cos of 2A, well, we've got 3 alternatives that we can use. If we go back up here, we could involve cos squared A, take sine squared A, or we could involve cos squared A, take 1, or 1 take 2 sine squared A. Because I've got sine A involved in my question, I'm going to use 1 minus 2 sine squared A. So this is 1 minus 2 lots of 4/5 squared. This is 1 minus 16 on 25 times 2, so that will be 32 on 25, and that's going to give me -7 on 25. In our last example, I'm going to use the double angle identity, which is 2 tan A over 1 minus tan squared A. So I've got 2 lots of, now the tan of A is going to be the opposite over the adjacent, so that's 4/3, divided by 1 minus 4/3 squared. So this is going to equate to 8/3 divided by 1 minus 16/9. It's going to give us -7/9. And this is going to equate to -24/7, or -3 3/7. So in our second question, if cos of 45 is equal to √2/2, let's determine the exact value of sine of 22.5. Straight away I notice that 22.5 is half of the cos of 45 degrees. So I'm going to rewrite cos 45 as 2 lots of 22.5. Now I've got sine involved, so I'm going to use the angle identity of 1 minus 2 sine squared of the angle. So if this is worth 2 lots of the angle and A is 22.5, then I've got 22.5 over here. So this is going to leave me with √2/2, which is cos 45, equaling 1 minus 2 lots of sine squared of 22.5. So √2/2, I'm going to rewrite this as take 2/2. This equals -2 sine squared of 22.5. Fortunately, I've just run out a bit of room, so I'll just pop it over to the right. So I'm going to just equate those fractions on the left. So I'm going to write them as √2 take 2/2 equals -2 sine squared 22.5. Now I'm going to divide by this -2. So that's going to make this a negative. So it's going to become 2 subtract √2/4 equals the sine squared of 22.5. And to get rid of the square, I'm going to square root this left and right side. And that's going to leave me with the sine of 22.5 equaling the square root of 2 minus √2/2. So a little bit of manipulation there. So let's have a look at solving involving these double or half angle identities. So we've got the sine of 2x plus the sine of x equals 0, and we're having a look between negative pi and pi. So starting with this double angle on the left, I'm going to replace sine 2x with 2 times the sine of x times the cos of x plus the sine of x equaling 0. I can see I can take a common factor out here of sine x. So sine x, and that will leave 2 cos x plus 1 equaling 0. So I've got a binomial here that I can solve. So sine x is going to equal 0, which means x can be 0 at 0 degrees and at pi or negative pi. Or I've got 2 cos x plus 1 equals 0, which means cos x equals negative a half. And this is going to happen as cosine equaling negative a half is going to be in the second and third quadrant. So this is going to be at negative 2 pi on 3 or positive 2 pi on 3. So now I'd like you to pause the video and have a go at question 4 and see if you can solve between 0 and 360 degrees. So in question 4 we can see that we can change that left side. I've chosen to change it to 2 cos squared x subtract 1. And I can see that I've got a quadratic set up with cosine here. And when I factorise that into the double brackets, I can get solutions of 120 and 240 degrees. So let's do a proof involving these identities. So I've got cos 3 theta equals cos theta in brackets 1 minus 4 sine squared theta. So I'm going to start with the left-hand side. But as you can see, I've got 3 theta. So what I'm going to do is separate that as into 2 theta plus theta. I think that's going to be much easier to deal with. So I'm actually just going to use the compound angle identity first here. So I'm just going to start with, this is going to be cos 2 theta times cos theta. And it's a plus, so it's going to become take sine 2 theta times the sine of theta. So now I've used the compound angle identity for cosine. I'm going to use the double angle identities for the cos 2 theta and the sine 2 theta. Thinking about the fact that on my right hand side I've just got a single cos theta and I've got a sine squared theta, I'm going to change the first one to 1 minus 2 sine squared theta. Hopefully that will bring in that sine squared theta in the right side, and that's times cos theta. And then I'm going to use the double angle for the sine 2 theta, which is 2 sine theta times cos theta, and I've got times the sine theta left on the end. So I can bring these sine thetas together to make a sine squared theta. So what I've got here is I'm going to expand this just to have a bit of a look. I've got cos theta take 2 sine squared theta times cos theta, take 2 sine squared theta times cos theta. So I can see that I've got some like terms here. So I've got cos theta take 4 sine squared theta cos theta, and then I've got a common factor here. So I'm going to take out the cos theta out the front, and I've left with 1 take 4 sine squared theta, which equals my right hand side. So now I'd like you to have a go at question number 6. Before you pause the video to have a go at this proof, I want you to have a look at the angles involved here. We have a sine theta, and we also have theta over 2 or half theta. So there's a big hint here to say that we've got a half angle involved here. So I'd like you to think back to our identities and how we can express them using that idea that on the left-hand side of that identity is, say, theta. So on the right-hand side, that would be a half theta, and how we can use that identity. So pause the video and see if you can work on perhaps the left-hand side to equate the right-hand side. So in looking at this proof, I've started with the sine theta and used that half angle identity. So 2 sine half theta times cos half theta, and that's times tan of half theta. I've then taken the tan and used the sine over cosine equivalent value, and I've been able to cancel out the cos theta on 2's in there, multiplied and divided. So that's left me with 2 sine squared theta on 2. And I've used the Pythagorean identity just because I noticed on the right-hand side that I'm dealing with cos squared. So the best way to get rid of sine squared is to use the Pythagorean identity here as 1 minus cos squared theta on 2, and expanded that bracket to equal our right-hand side.